The Madness Tech community connects tech enthusiasts in the field of data, front-end, product and cloud native. Twice a week, on Mondays and Wednesdays, you can find new talks and interviews from the community on this channel. Subscribe now and feel free to join our community and meetups. Events and groups are listed below, and now follow us into the rabbit hole.
Hi, my name is Bastian. I'm a field engineer at SUSE, and there I mainly focus on everything related to containers, Kubernetes and our Rancher products. Today I want to show how you can manage everything from 1 to 1 million of Kubernetes clusters sensibly with Rancher. Before we get started and go into the details there, I want to start with talking quickly about containers. Containers are great because they allow us to package our applications into self-contained packages, images that are portable and that contain everything that our application needs to run. The whole source code, compiled binaries, libraries, all the dependencies that I need. And when I packaged my application in such an image, it is very easy to take this image, put it on any kind of server, virtual machine, device that has a container runtime and just start it. I only need the image, I only need a container runtime, nothing else. And when I don't need this application anymore on this device, I can stop it. Perfect. And I have a clean system again. And containers are awesome. It's easy to start them up and stop them. And if you have 1 or 2 of them on 1 or 2 servers, starting and stopping them, deciding which container should run on which server, how to set up network and so on, is fairly easy. But if we look at reality, very quickly we can see that you not only are running for any kind of real life, real world application, you are not only running 1 or 2 containers on 1 or 2 servers, but you quickly end up with lots of containers because you have maybe more than 2 servers, maybe like a dozen or 20 or 50 or a few hundred. You also may be using a service-oriented architecture, microservices or something like this. So you have multiple applications that communicate and talk with each other. And then you also have things like monitoring daemons, logging daemons, security scanning, databases, and lots of auxiliary things that also need to run somewhere and need to be managed. And containers are also great for that. But then it gets a lot harder to decide, okay, which container should run where on which servers in order to use the resources that I have as efficiently as possible. And then setting up networking, security, and even automating the starting and stopping of the containers on the right servers can become quite a challenge. And that's why we have things like Kubernetes. Kubernetes is a container orchestration system that you can install on your servers, on your system, and then Kubernetes decides on its own, okay, which containers should run where and how they should be set up. And the great thing about Kubernetes is you can think of it as a standardization of a compute platform. It can run on basically any infrastructure, from your developer laptop to your servers or virtual machines in your data center, to the big and small cloud providers, as well as in edge scenarios and like IoT devices, factories, the industry PCs in there, 5G cell towers, cars, planes, even satellites in space. Wherever you need to run software, Kubernetes can be the platform that standardizes and automates it. And on all these different infrastructures, Kubernetes then provides a standardized and common API that not only helps you to start and stop containers and deploy update containers on the infrastructure, but it also cares about health checks, load balancers, overlay networking, security policies, service discovery, backup and disaster recovery, role-based access control, and so on. So this is great. And Kubernetes can really help you a lot by not reinventing the wheel all the time and spend hours and hours and weeks on writing and maintaining deployment scripts or monitoring integrations. But when you actually start to use Kubernetes and see the benefits of it, you also have to manage Kubernetes itself. And nowadays, with modern distributions, it's actually not that hard anymore to manage 1 or 2 Kubernetes clusters. No problem. But then, especially in the edge, but also in more traditional hosting environments, you quickly end up not only with 1 or 2 Kubernetes clusters, but with multiple one of them. Why is that? First of all, usually you not only have a production environment somewhere, but maybe a development environment, maybe 1 or 2 staging environments, and you very likely want them cleanly separated. That means 1 cluster per environment. Especially in development, you could also think, okay, why not even make 1 cluster for each development team so that they don't influence each other, and team A, when they deploy something, destroy something, is not negatively affecting team B. This actually also could be a reason why you want to have multiple clusters in production. If you have third-party software vendors, you may want to cleanly separate what they are doing in their Kubernetes clusters to what you are doing with your software. It could also be that you have multiple data centers, and then each data center gets 1 Kubernetes cluster. Maybe also in multiple locations on multiple continents. Or it could be that you have some workloads, like machine learning algorithms, that you maybe want to put on different hardware, completely separated, maybe even on a cloud provider somewhere, and separated from your actual web applications. So tons of reasons why you may end up with more than 1 or 2 clusters. And we haven't started talking about edge devices and IoT devices yet, where the clusters quickly grow into the millions. And then managing all of these Kubernetes clusters by hand can become quite a challenge as well. So we need something like a management tool for a management tool. And that one is Rancher, or one of the possibilities is Rancher. Rancher is a multi-cluster Kubernetes management tool where you have a central platform, a central UI, a central API with which you can, first of all, provision new Kubernetes clusters regardless on the underlying infrastructure, regardless of the Kubernetes distribution. And you can manage them, upgrade them, but then also manage things like authentication, authorization, monitoring, log management, security policies, audit logging, all from a central point of view. So this makes it really powerful and a lot easier to make sense of all of these Kubernetes clusters. And we are going to have a look at how this works then also in a small demo later on. Before we go into the details there, let me quickly also talk a bit more on Kubernetes at the edge. Because with buzzwords like Industry 4.0, this is where a lot of DevOps innovation is currently happening and where a lot of organizations and companies are seeing huge benefits of adopting things like Kubernetes that they're already using in the cloud, in their data centers, also on the edge. But one problem where the edge is different than a traditional data center or a cloud provider is that we have very limited resources usually. In our data center, we probably have very beefy servers with lots of CPU, lots of RAM, lots of disk space. And in cloud providers, it's basically for most use cases nearly unlimited what I can use there. On an edge device, on the other hand, I may have only maybe a tiny Raspberry Pi, a tiny 2 CPUs, 4 gigabytes of RAM device, but then a lot of them. And on the other hand, if we look at the architecture of a typical Kubernetes cluster, the default architecture is more targeted to these data center and cloud environments. In a simplified view, in every Kubernetes cluster, we have a Kubernetes control plane here in the middle. This is basically the Kubernetes API with which we as a user, as an administrator, talk to tell Kubernetes what containers we want to be running in the cluster. Kubernetes then stores what it should be running and also the current state of the cluster in its own data store. This is usually an etcd data store, which is a distributed key value database. And then you have all the worker nodes in a Kubernetes cluster. These worker nodes are then actually running your application containers, and they also constantly communicate with the Kubernetes API to ask, hey, Kubernetes, what are the containers I should be starting? What are the containers I should be stopping? How should I set up the network? And so on. And they also report back their status. And this diagram here is even simplified because the Kubernetes control plane in the middle is consisting usually of multiple different microservices that you can then also scale independently. And there you first of all have to run all of these microservices, you have to configure them consistently, and you have to ensure that the communication between them happens securely. And each microservice, each component of a Kubernetes cluster needs, of course, CPU and RAM, and quite a bit already actually. In a cloud environment or in your data center, that usually doesn't matter because compared to what your databases and your web applications need in terms of CPU and memory, the control plane of Kubernetes is fairly insignificant compared to that. On an edge device where I have tiny devices, lots of them with small applications, putting the whole Kubernetes control plane, all the Kubernetes components on them, would basically take more than half or a lot of CPU memory compared to the applications running on them. To solve this challenge and to still make Kubernetes a good way to work in limited resource environments, we created K3s. K3s is a lightweight Kubernetes distribution, especially tailored for the edge. Of course, it also works on virtual machines in the cloud in the data center, on bare metal as well, but it's especially made for the edge and edge devices where you have limited resources available. And what's special about K3s is it's a very opinionated distribution, because everything that you need to run Kubernetes is contained in a single binary. That includes the data store, either an SQLite or etcd database. It contains the container runtime, the networking plugin that is used to set up a network between all of your containers, an internal DNS server, all the host utilities that are needed, storage providers, and so on. Everything is within one binary. That means it first of all works very well also on a single machine in a single device cluster. If you have one 5G cell tower, you usually have one small device in there, and if that one is down, also the cell tower is down, so you don't have high availability there. But it also works in a highly available fashion. K3s is very opinionated, but still all components are swappable if you need to do different decisions. The great thing is, because of combining everything in a single binary, K3s can make a lot of optimizations. For example, it can share caches, it can share HTTP servers, and reduce the amount of CPU memory you need to actually organize and manage the runtime of every one of these components. And this in turn reduces the CPU and memory footprint of a K3s cluster significantly compared to a standard Kubernetes setup. It also makes it very fast and easy to set up. You will see this in a second. Has full ARM support, also good and important for edge. And of course, when you use it, it behaves like any other Kubernetes cluster. So K3s is different in how you set it up. and how it's architectured internally. But from using the Kubernetes API, it works the same way as any other Kubernetes cluster and is also certified by the Cloud Native Computing Foundation to be completely standard compliant. So a typical edge setup could like this. I have the central Rancher management server here that ties all the different edge devices, all the different K3s clusters, and also maybe our cloud and on-premise clusters together, and manages all of that from a central point of view. And then you have down here attached to this all the independent edge clusters. Every one of these edge clusters is autonomous and they can look significantly different. It can be single node clusters as well as highly available multi-node clusters. Let's have a look at this. So if you go back from the slides here, you can see here in this window, I have a view of an installation of the Rancher management server. We are seeing the Rancher management UI here, but rest assured, everything I'm going to click around here and show you is also completely automatable. There is an API behind this, so you don't have to click. And especially if you're managing tens of thousands or millions of clusters, you also don't want to click anymore. So you can completely automate everything. You can also see there are a couple clusters here already registered at Rancher. And let's see how fast and easy it is to add a new cluster to our central management system. In this other window here, I'm connected already to, in this case, a virtual machine running on AWS, but you can think of this being an edge device. It's actually also running as ARM CPU, so it's fairly similar to a small edge device. The VM is running a Linux, and let's make this a bit bigger so that it's easier to see. And it's basically just running the standard services, DHCP, systemd, SSH daemon, cron daemon, basically very bare bone Linux. And if I want to now install K3s, all I have to do is execute a small installation script. And all this installation script is doing is making my life a tiny bit easier, because based on a release channel information, it's finding out what is the newest stable K3s version. It downloads the K3s binary and a checksum. It verifies then that the binary hasn't been modified. It also downloads the binary with the right CPU architecture. You can see this here. It's then putting the binary to user local bin. For convenience, it's also creating a couple of symlinks for other CLI tools that are embedded within K3s. And it's creating two small scripts to completely stop and to completely uninstall and remove K3s. And then it's creating a systemd service and starting it. So I can also easily not use this script, but put this into my own Ansible, Terraform, whatever automation. And now we have a up and running Kubernetes cluster on this small VM as a single node cluster. If I now want to create a highly available K3s cluster, I basically execute the same script on other servers, and then I provide one or two more arguments telling K3s not to create a new cluster, but to join an existing cluster. You can read up on this in the documentation, and you will see also the links to it later on in the slides. So my Kubernetes cluster here is up and running and ready. I want to put this now into our central management. And all I have to do is here to click Add Cluster. And from the different options to create new clusters within the Rancher management system, I say, okay, please register me an existing Kubernetes cluster in my central management. I can give this cluster a name. And then I can, of course, decide which users within Rancher should have access to the cluster and which permissions they should have in the cluster. But the important thing here is that I also can put some labels on the cluster. And these labels are basically additional metadata that I can use to quickly identify my cluster later on, which gets very important if I have more than 2 or 3, but tens of thousands of them. So for example, I can freely decide which labels I want to add. So I could add a label saying this is a cluster with an ARM CPU to quickly identify all clusters that are running on ARM. I also could put in a label telling where the cluster is located. So maybe I can add a location label with the value West, because it's in West Europe. Notice I made a tiny typo here. I made this on purpose, and we can see what happens if you correct it later on. And I could add and modify any labels at any point in time. And if I click Create Now, I get a small import statement, which I can use then to deploy a small Rancher agent into my cluster. So basically this manifest that was generated here, I'm applying this to my cluster, and this deploys a small agent. And this agent then is starting just a container inside of my cluster here, which connects back to Rancher and makes this cluster now configurable and manageable in our central management interface. The nice thing is everything that is Rancher specific here, or the only thing that is Rancher specific here in our small edge cluster is this agent. The cluster is still completely autonomous, and the central management is not in the way for communication or for running any of the applications inside of the cluster. That means if the connectivity between my edge device here and the central management over here is not working because someone cut the network cable, my cluster is still up and running and is serving my workloads. Everything is working fine. I just can't see it, or I can't manage it from the central management interface anymore. I can still make a lot of changes. We can also have a look at this later on. But they are not directly applied then to this edge cluster because it's currently not available. It doesn't have any internet connectivity maybe. But as soon as it comes back, this agent here connects back to Rancher, to the central management, and then pulls in all the new changes and do all the necessary adaptations. And you can see the cluster here is up and running. I can click on it. I can see some statistics and details. I can get myself a kubeconfig to access this cluster now from other machines. And I also can, in the UI, look into the cluster and in the Cluster Explorer, check, for example, which pods and which containers are running in my cluster, and can now start deploying new ones through an intuitive UI. I can also debug them, look at the logs directly here in the UI if I have the permissions to do so. Okay, let's get back to the slides. Now that we saw how fast and easy it is to create a new cluster with K3s and also add them to a central management, let's talk a bit more what it actually entails to also manage workloads on thousands of clusters. Because the likelihood is that if I have thousands or tens of thousands or millions of clusters, that I have workloads that I just want to deploy on every one of them. Maybe with slightly different configurations in terms of host names, IP addresses, passwords. But if I have a lot of 5G cell towers, I want to deploy the same applications on all of them. A central management system can be a great starting point, because what I can do is I can ask Rancher, hey, give me a list of all my clusters with all the information I need to connect to the Kubernetes APIs. And then in a naive approach, I can just, in the script, iterate over all of them. And every time I want to deploy a new version of an application, I connect to every one of those Kubernetes APIs and tell these Kubernetes API in a loop of every cluster, hey, please update this deployment, please update these containers. And this will work. But it can have a few downsides. If I just have a naive loop over all of my clusters, and I have thousands of them, this will actually take a significant amount of time just because of all this network communication that is happening. It gets even more complicated if we have devices where the internet connectivity is not very stable, because the likelihood of running into connectivity issues during a deployment can become quite high. Which means I have to then also react on failures of a deployment to a cluster. I have to remember then in my scripts that I haven't deployed a new application version to this cluster, and I have to retry it later on. And later on could actually be days in edge scenarios, because maybe some industry PC, some factory, some cell tower is powered off for days and not just minutes. And of course, this is all solvable. I can write scripts for that. I can make this a lot smarter and put a lot of work into this to solve all these problems. Or I can have a look what Rancher maybe has to offer for that. Because Rancher not only allows you to manage each cluster individually, you can also manage them and the workloads in them directly in groups with a multi-cluster continuous delivery tool that is based on GitOps principles. What does it mean? Here in the middle, I have my central management tool. This would be Rancher. And Rancher also contains a continuous delivery portion. You have down here all your clusters that are registered on the central management, and you saw this already before. But what you haven't seen yet, that you can then also group these clusters together to make them easier addressable. So for example, you could say you're creating a group of clusters that have an ARM CPU. Or you could say you create a group of clusters that are in the location west. Or you could say you create a group of clusters that group all clusters together that are dedicated to a certain end user or customer. And one cluster can actually also be in multiple groups, so you are very free in organizing all the clusters in a sensible way. And then you can register as many Git repositories to the central continuous delivery tool. And these Git repositories contain then the Kubernetes application manifests, Helm chart packages, customized packages, basically the configuration, the declarative configuration that tells Kubernetes what should be deployed, what should be configured in each cluster. And you can register these Git repositories that contains this information directly here in the central management interface. And then you can configure which clusters or cluster groups should pull this information in and then actually deploy this manifest in their cluster. And first of all, the central continuous delivery tool will always pull the information from the Git repositories to see, okay, what has changed? Is there maybe an update to it? And it will provide this information then to all clusters and cluster groups. And the cluster and cluster groups will then pull this information, what they should be running, from the central management as fast as they can. And if one cluster or a group of clusters is offline, of course it will get out of sync if you change something here. But as soon as it becomes online again, it will pull the new information and update itself to the current state it should be running in. And of course, you also have then central visibility, which clusters are up to date, which cluster groups are up to date, and which are not. Let's have a look at this. And if we now go here into Rancher, we have one section in here, which is called continuous delivery. And in this continuous delivery tool, you can see you have all your clusters in here. For example, my 4 fleet clusters. And you have then the availability and the possibility to create cluster groups of them. So for example, I could create a cluster group called ARM that matches all clusters with the label CPU and the value ARM. And that matches 2 of the cluster of my 10 existing clusters. Or I could create a cluster group, maybe called Edge clusters, that have a label location that just exists regardless of the value, which matches 3 of my 10 existing clusters. And I can create as many groups as I want. Next, I can create Git repositories in the continuous delivery system. And this means I can create here a Git repository to register an existing Git repository. And I have already prepared one on GitHub. You can see here, this is a repository. This is publicly available on GitHub. You can also check it out later on after the talk. And one thing you can see here is that this Git repository contains an empty folder called Edge Cluster. So let's maybe create this repository here now within Rancher. So I put in a name, the URL to the repository. I can choose the branch or a specific revision that Rancher should watch for changes. I can of course set up authentication in case this would be a private repository, and I can also configure the TLS settings in case this would be a self-hosted Git instance, like a self-hosted GitLab, for example, with my own private CA. And then I can choose if I want to watch the whole repository or only certain subdirectories like my Edge cluster folder. Next, I can choose which clusters the content of this repository and this subdirectory should be deployed to. Either I can say, please deploy to all my clusters in here, or to a single cluster, or maybe only to a cluster group. So let's deploy it to the Edge cluster group. And if I click Create Now, the repository is registered, and nothing will happen because my directory here is still empty. Let's change that. So here I have a local clone of the same repository, and you can see the empty Edge cluster folder here. And let's maybe put in a Hello World application. And let's directly commit and push this to GitHub. Perfect. And you can see now that I have a new folder here, Hello World, and this in the end just contains standard Kubernetes manifests. If you're familiar with Kubernetes, you should recognize this. If not, it's not that important for our demo here. It basically tells Kubernetes, hey, please run this container image here 2 times. Open up port 8080 on them. It also configures an environment variable for the container, and it configures a health check. That's basically it. I also have a service in here. With a service, you can think of it as an internal load balancer of Kubernetes, and this makes the port 8080 of the container available directly on this port 30001 on every node of my Kubernetes clusters. And if we go back to Rancher, we can see, oh, that worked. I have now in 3 clusters a new application deployed. And we can also have a look at this. If we go back to the Cluster Explorer here and we go to our fleet, let's say 0 cluster, we can see we have now, let's go only to the username spaces. We have now our Hello World application running here with 2 replicas, and we also have a service that is the load balancer for this application. And if we click here on the port, we can directly access our application, which does some XHR requests to the backend and shows us nice cows with purple backgrounds. And let's maybe do a small experiment. What happens if we maybe change something in here? So let's go into the deployment YAML, let's edit it, and let's change the color maybe here to green and commit this back to GitHub. So here you can see the color changed now. And in a few seconds, we should see, if we go back to our continuous delivery tool, that the continuous delivery system is now pulling in the new changes, updating our application and updating the deployment in here. And it's then in the end doing a rolling update on every cluster to change the environment variable from purple to green. And you can see now the rolling update is in progress. And if we check back in our demo application, you can see the first green cows appearing here. So every time we change something in this repository, this gets rolled out to all attached clusters. And this works the same way if we change the cluster configurations. Remember back when we added our fourth cluster to Rancher, I made a small typo in the label. Let's maybe correct this and see what happens. So here I have my Fleet 3 cluster and I can edit the configuration from here. And you can see the typo in the location key of this label. And if I fix this, click Save. This Fleet 3 cluster is now also part of our Edge clusters cluster group here. And if we go to the Git repository, we can also see that our Hello World application is now being rolled out to the Fleet 3 cluster as well. And I actually can do a lot more with the system. So I can not only put in plain Kubernetes manifests like these into the Git repositories. I can also put in Helm charts. I can reference Helm charts from other repositories. I can use customized packages, basically everything that Kubernetes usually uses and understands. And one other feature that this continuous delivery system also has is that I not only can put in manifests or Helm charts or whatever that gets rolled out the same way to all clusters. I can also put in information that tells the continuous delivery system, hey, let's maybe do a pull first to pull in the changes I made earlier. And I can also use the system then to say, hey, please roll out the same deployment, the same application here to all clusters. But on some clusters, for example, on the clusters in the location west, please put in an overlay and configure them slightly differently with different Helm values or with some patches who, for example, patch the color here to green. And in order for that to make any sense, I should maybe change it back here to purple. So some clusters will have a color purple, some clusters in a different location will have a color green. So let's commit and push this. And if that was all a bit quick, let's quickly revisit what we added. And I should of course put this into the right folder. Sorry about that. Let's commit and correct this and push this again. Okay. Now it may, let's check it here. Unfortunately, I closed this. But what we added now, we still have our deployment YAML and our service YAML. We created an additional Fleet YAML file here. The deployment YAML now has again the cow color purple in it. And the Fleet YAML says, okay, I want to have a customization, which is called West, which should add an overlay to our application here for all clusters that have the label location West. And these are 2 of my 4 clusters. And if we check how this overlay is looking like, this overlay here called green color is patching the deployment YAML and it's changing the environment variable cow color to green. I can do the same thing then also with Helm values or with customized packages. And if we go back to Rancher, we should see now that if you go back to the Cluster Explorer and open up maybe also the Hello World application here in Cluster Fleet 1, that this cluster here has purple backgrounds and this cluster here has green backgrounds. So a very powerful tool. Okay, that's basically what I wanted to show you. I wanted to show what we have seen now, how easy it is to create new Kubernetes clusters, especially also on edge devices. We saw how you can put them into a central management system and how you can use the system then to manage these clusters and to also deploy new applications to them in a GitOps way from a central point of view to a lot of clusters. We barely scratched the surface, so there are a lot of things in there in terms of monitoring, logging, service meshes, security policies, role-based access control that are all also very interesting. Further information you can find here on these resources in the docs from K3s, Rancher, the continuous delivery system, and of course here's also the Git repository with all the examples. And you of course can also reach out to me over Twitter. I'm available there on twitter.com/Bastian Hofmann. Very easy to remember, very not very imaginative. Feel free to reach out, ask any questions you want, and thank you for attending this talk.